All right, so today we're going to be looking at changes of state, phase changes, the heat of vaporization, or the heat of fusion, kind of what these mean. So uh, last time we kind of looked at how much energy was required to change the energy, change the temperature of an object, and how much energy that would take. So for water, we knew it took 4.184 joules per gram degrees Celsius. That's the specific heat of water. And so if I have 1 gram of water, if I give it 1 joule of thermal energy, it'll change degree by 1 degree Celsius or 1 Kelvin. And then we can also use it to figure out changes in temp. Or if I don't know what the substance is, there's ways that I can figure out what its specific heat is to help, hopefully, let me figure out just what that material actually is. So today we're going to be looking at uh, what if we're talking about like liquid ice? So ice, water, we know has a freezing point of 0 degrees Celsius and a boiling point of 100 degrees Celsius. So let's say that I have a chunk of ice and I supply some heat to it. We're going to pretend that's fire. I want to know how much energy does it take to block, and let's say that I even have a 50-gram block of ice. I want to know how much energy does it take to turn that ice solid water into liquid water. So the equation we're going to use here is Q equals mL. This is a very, very basic equation where Q is still equal to heat or heat energy. It's measured in joules. Mass, which is in grams or kilograms. Big thing though is whatever unit the mass is in, it just has to match this capital L, which we just got done using capital L to mean length. This time capital L means latent heat. Essentially, specific heat was how much energy was required to change 1 degree Celsius for 1 gram of substance. Latent heat's kind of the same thing. It tells us how much energy is required per mass of a substance in order to get it to just change state. So the unit for this one is actually going to be, let's see if I can remember this right. It's joules per gram or joules per kilogram. Right, so it's a lot easier, I would say, even than the specific equation. Um, Really, why we don't need to worry about temperature or anything is when ice turns to water, there's no change in temp. That's all occurring at a temperature of 0 degrees. Um, Really, what we would find is like if we say that's temperature and this is energy added to the substance. Um, Give me one second. Okay. So starting off with, we could say our ice just kind of maintain, we could say that the ice increases to a certain temperature, and then we're going to say that's 0 degrees Celsius. Once it hits 0 degrees Celsius, any extra energy that's added to it is going to go from turning that ice into water. So at this point, this is where ice is becoming water. Solid to liquid. Then eventually, when all the ice melts, and only when all the ice is melted, that's when the energy will start raising the temperature of the water until we say it gets to about 100 degrees Celsius. And at that point, all of the extra energy that's put into it is used to turn that water into steam. And then once all the water's been turned into steam, then the temperature can raise again. The big thing though is when the phase changes is occurring, when melting is occurring, when boiling is occurring, the temperature's not changing. So when you go to boil a pot of water, once it gets to 100 degrees, that water can't get any hotter. Essentially, it's just going to be turned into steam. Um, so let's come back up here. So we said that we had an ice cube with a mass of 50 grams, and we wanted to know how much heat energy is needed to turn it into water. L, capital L, that's something that you're going to find off of some reference materials. You can find it online. The really in this case, so the two things that we kind of have is just to further complicate it. So that capital L, the latent heat, we have latent heat of fusion. Fusion would be like kind of this applies to freezing or melting. Really, we kind of look at it as kind of the freezing where the molecules, the atoms, are kind of fusing together into a solid. So this will be melting or freezing. The other latent heat we have is the latent heat of vaporization. This would be boiling or condensing. You know, when we have it as a gas, condensing down into a liquid. Okay, so the heat of fusion, that's how much energy it takes to melt the ice. That's also how much energy would need to be taken from the water to get it to freeze. Okay, so every substance is going to have a value for the latent heat of fusion and a value for the latent heat of vaporization. If I'm talking about ice melting, if I'm talking about 50 grams of ice melting, uh, I'm using the heat of fusion. If I'm talking about 50 grams of water boiling, I'm using the latent heat of vaporization. All right, so coming back up here, uh, 50 grams of ice. Okay, I know that I'm going to use the latent heat of fusion for this one because I'm talking about ice melting. The latent heat for this one, I go ahead and check my reference material. I find that the latent heat of fusion for water is 334 joules per gram. Okay. Uh, my first mass was in grams, my latent heat's in grams, so I'm good to go. So now I just need to plug my numbers in. So if Q equals ml, mass I have is 50 grams. Latent heat we said was 334 joules per gram. Now if I even do my dimensional analysis, my unit analysis, I've got grams here, joules over grams here. My grams will cancel each other out, and I'm left with joules. That's what energy is measured in. So I know I've at least done that part right. So if I bring up my calculator, bring it over here. So I've got 50 times 334, 16,700 is what that equals. So to turn 16,700 joules of energy in order to turn a 50 gram ice cube from solid water or ice into liquid water. And really, you know, this seems like it's a lot of energy. Um, and it kind of makes sense. So, you know, once spring comes, you know, it takes a lot of time for ice on lakes to melt. It's because that energy, all the energy given to the lake, has to turn all of that ice. First, has to get the ice up to 0 degrees Celsius, and then the energy has to turn all that ice into water before the water can change temperature. Now, if you get a big enough body of water, there's things like convection stuff that's going to throw it off, and physics. So we're going to keep it kind of looking at isolated incidences, looking at small things we can kind of control. Um, so let's say that water, let's even keep it going. So now I've got 50 grams of water. We're going to call it liquid water. Okay. I want to know how much heat energy is required to melt it. So this would be, oh, sorry, not melt, to boil it. Okay, so down here I'm going to look at boiling it. So in this case, the heat of fusion, sorry, the heat of vaporization. Up here I use the heat of fusion. So down here, I'm going to use the latent heat of vaporization. I check the reference chart. Let's say that that water, if I'm looking at that right, has a latent heat of vaporization of 2,260, and that's still in joules per gram. In this case, Q, that heat energy is still equal to mass times latent heat. In this case, my mass is 50 grams. Latent heat of water we found out to be 2,260 joules per gram. And so this case, just have to take those numbers times each other. So 50 times 2260. This time, though, it takes 113,000 joules of energy. So 113 joules of energy. All right, so same masses of H2O, same masses of water. However, it's a lot easier to get water to melt or freeze than it is, by easier, I should say, it takes less energy to get water to melt or freeze than it does to get water to boil. Um, Really, this kind of goes into a little bit of chemistry where we're looking at um, here, we're just getting molecules that are attracted to each other to kind of either lock into place or to kind of just be able to slide past each other. Down here, the latent heat of vaporization, here we need to give these molecules enough energy that they overcome all of the intermolecular forces that are holding them together so that they're able to escape being in a liquid, being able to just fly around randomly as a gas. Typically, what we'll find is your latent heats of vaporizations will be higher than your latent heat of fusions, just because you have to completely overcome those intermolecular forces. Um, Let me come down here. Let me just add that that's melting, that's boiling, 50 grams of water. Uh, we could have done this with methanol, mercury, methane, lead, anything that we can have uh, solid liquid gases of. Some substances, we can't get solidified, things like helium. So in which case they only have a latent heat of vaporization. Um, Pretty much you should have reference materials to help you out with this stuff. But I know I kind of rambled on and kind of went a roundabout way of actually getting to the problem. But that's that. Good luck with the practice.